Hi everybody, in this lesson we're going to derive the half angle identities and use them in a few examples together. And let's start by looking at the identity for the cosine of 2 theta. Now we've already developed this identity and we've seen it before. And let's take a good look now at the 2 theta and the theta. See, what's important for us right now is not the whole identity itself, but the fact that the angle I show here is twice as big as the angle I show here. That means that this angle is half the size of that one. And so what we're going to do is replace the 2 theta and the theta so that instead of looking like an angle and its double, it looks like an angle and its half. So I'll replace 2 theta with x, and I'll replace the theta with x over 2. Now, this is okay because the relationship between these two is still the same. This one's twice as big as that one, and in this version, this one's twice as big as that one. Now, in order to make this one easy to use for a half angle, what we're going to do now is just solve this equation for the cosine of x over 2. So I'll start by adding 1 to both sides, and then I'll divide both sides by 2. And so you can see that if I divide the right side by 2, the 2 will cancel out, and if I divide the left side by 2, it will show up in the denominator. And the only thing left to do now is to remove the square notation, so we'll do the square root of both sides. When you do the square root of both sides, you're required to put in this plus minus. Whenever you do the square root of both sides, it takes that plus minus to make everything alright. Now, the sign of our answer will be determined by the location of the angle, x over 2. Not the location of x, but the location of x over 2. You know, just like we've always done, the sign of the function is determined by the location of the angle. Okay? That's our first half angle identity. I can use this identity to find the cosine of half of any angle whose cosine I already know. For example, if I needed to know the cosine of 15, well, 15 is half of 30, and I already know the cosine for 30, so I could use this to figure out the cosine for 15. Now let's develop the identity for the sine of x over 2. We'll start with another cosine of 2 theta identity, this time the one that has the sine of theta in it. And again, we'll do the same trick where we'll replace the 2 theta with x, and we'll replace the theta with x over 2. And again, we will solve this identity so that it says sine of x over 2 equals. So I'm going to now subtract 1 from both sides and divide both sides by negative 2. Alright, now this is okay, but it's a little awkward to have a negative like that in the bottom. What we should do is multiply both top and bottom by negative 1. If we multiply the top by negative 1, we'll have negative cosine x plus 1, which I will write this way so that the positive term comes first. And if I multiply the bottom by negative 1, I'll have positive 2. Right, this is much nicer looking. And now let's get rid of this square by doing the square root of both sides. And don't forget, that requires us to insert the plus or minus. And we will determine whether plus or minus is required by the location of x over 2. Now that we have our formulas for the sine of half an angle and the cosine of half an angle, let's develop a formula for the tangent of half an angle. And we're going to take a little different tack this time. The last 2 times we've doctored up our cosine of 2 theta identities. This time I do not have a cosine of 2 theta identity that contains a tangent, so I can't do the same thing again. And if you look at the tangent of 2 theta identity, we definitely don't want to mess with that. So this time what we'll do is we'll go through the quotient identity. We know that the tangent of any angle is equal to its sine divided by its cosine. That means that the tangent of theta over 2 is equal to the sine of theta over 2 over the cosine of theta over 2. So we have formulas for these two things. Let's just plug in those formulas. Sine of theta over 2 is the square root of 1 minus cosine over 2. And the cosine of theta over 2 is square root of cosine theta plus 1 all over 2. So all I've done is plug in my half angle identities. And we definitely need to simplify this. This is really the formula we're after, but it's just not in a very nice form. So we're going to make it look nicer and easier to use. I'll start by using the quotient rule for radicals to put both of these together under the same radical. And once I do that, I can see that under here I've got just a big complex fraction. I need to get rid of these denominators. So both denominators are 2. Let's multiply top and bottom here by 2 so that our little denominators will cancel out. So these 2's are going to cancel and these 2's are going to cancel. And that will leave us with the square root of 1 minus cosine theta over 1 plus cosine theta. And again, we have this plus or minus outside our radical. The sign that we need to use will be determined by the location of theta over 2. Now, this is the formula we just developed on the last screen, and it's okay. I mean, I guess we have other formulas with radicals in them, but honestly, we do try to avoid the radical formulas whenever we can, right? Because radicals can be fussy and sometimes difficult to use. So if we could develop a formula for tangent of x over 2 that did not require a radical, that would be a good thing. Well, here's what we're going to do. If we multiply by the conjugate of this denominator, let's see what happens. Remember that a conjugate is the same two terms but with a different sign. So if I multiply the bottom by that conjugate, I'll also have to multiply the top by that conjugate. And now let's use FOIL method on the top and then on the bottom and see where that gets us. In the top, well, 1 minus cosine times 1 minus cosine is, I'm not really going to FOIL it out, I'm just going to leave it as 1 minus cosine squared. In the bottom, 1 plus cosine times 1 minus cosine, when you do use the FOIL method, you're going to end up with 1 minus cosine squared. Alright, now let's see what we can do to this. We know that 1 minus cosine squared, according to the Pythagorean identities, is the same as sine squared. You remember that 1 minus cosine squared is equal to sine squared. Okay, now the reason I wanted to do that is because now I have two squared quantities under this radical. So when I simplify the radical, the square root of a square just gives you what's being squared. So this is going to simplify to 1 minus cosine over sine. And now that we've simplified the radical, the plus or minus is no longer necessary. And the sign that we come out with just naturally from the formula will be the correct sign. And you won't have to choose the sign of this answer based on the location of this angle. It'll just naturally happen. Now this is one way that this formula could have been simplified. We also could go at it like this. Rather than multiply by the conjugate of the bottom, we could multiply by the conjugate of the top. You see? So I could multiply top and bottom by 1 plus cosine x. If I do that, 1 minus cosine times 1 plus cosine gives me 1 minus cosine squared. And in the bottom, 1 plus cosine times itself gives me 1 plus cosine all squared. And again, 1 minus cosine can be exchanged for sine squared. Or 1 minus cosine squared can be exchanged for sine squared. Now, since both things under the radical are squared, we take the square root of each of those squares, and we're left with sine over 1 plus cosine. And again, there's no longer any need to worry about the plus or minus. So I have these two formulas. I can use either one I like. I think they're both kind of the same amount of work as far as I can tell, but either one is a good choice. And either one is probably a nicer choice than what we had up here. Wouldn't you agree? So if I have three versions of this identity, one being this radical and another being this fraction and another being this fraction, I think I like these two better than the first one. So here are all of our identities that we have created so far. We have the cosine of half an angle, the sine of half an angle, the tangent of half an angle. Notice that all of these contain radicals, therefore their signs must be determined by the location of the half angle. Not the location of A, but the location of A over 2. And then we have these two alternate forms of tangent of A over 2. So, and both of these are probably going to be nicer and easier to use than that first one. Now let's take a look at a few examples together. This one says, find the exact value of the cosine of 15 using the half angle identity for cosine. Alright, let's take a look at that identity. Here's the half angle identity for cosine. So if we need to find the cosine of 15, then cosine of x over 2 needs to be our cosine of 15. X over 2 is 15. Well, if 15 is x over 2, what does x have to be? If x over 2 is 15, then the x must be 30. 30 over 2 is 15. So we'll plug in 30 everywhere we see an x. So the cosine of 30 over 2 is going to be the cosine of 15 equals plus or minus the square root of 1 plus cosine 30 all over 2. And let's substitute the square root of 3 over 2 in place of cosine 30, because we know that that is the value of cosine 30. And now you see that my answer contains a complex fraction, and you just can't leave that in your answer. So let's simplify here by multiplying everything by this denominator. I'll multiply every term by 2. So I've multiplied the 1 by 2, and the square root of 3 over 2 times 2, and the bottom times 2. In the top, 2 times 1, of course, is 2. And in this fraction, the 2's cancel out and leave us square root of 3, and in the bottom, 2 times 2 is 4. And this is our simplified form. And I know it's probably bothering you a little bit that we have a radical underneath a radical, but that's okay. That is considered just fine. And we don't have to do any simplifying for that. So we'll say that this is our final form of this answer. And by the way, if you were to take out your calculator and punch all of this in, 2 plus square root of 3 equals, and then divide that answer by 4, and then do the square root of that answer, you'll see that the decimal value you get is equal to the decimal value for cosine of 15, even though it's different looking than the last time we found the exact value for cosine of 15. That's okay. Alright, this time let's find the exact value of the tangent of 22.5 using a half angle identity. So I need to pull out the identity for the tangent of x over 2, and I have three choices here. And so which one should I choose? Well, I guess the one that's the easiest to use. Probably this top one is not easiest to use because it does involve that radical. But these other two is kind of a toss-up, so whichever one you think you like best. Now let's think about 22.5. If 22.5 is half of something, well then that something must be 45. 22.5 is half of 45. So 45 is going to be what we substitute in place of our theta here. And let's just use this middle identity. So the middle identity says sine of theta over 1 plus cosine of theta. We've figured out that theta is 45. So that's going to be sine of 45 over 1 plus cosine of 45. Sine and cosine of 45 are both square root of 2 over 2. And again, our answer contains complex fractions. We must simplify to remove those. So we'll multiply the top and both terms in the bottom by 2. And so in the top, the 2's are going to cancel, leaving me square root of 2. In the bottom, as I distribute this 2, 1 times 2 is 2 here, and square root of 2 over 2 times 2 is square root of 2. The 2's cancel. Okay, now I can't leave my answer in this form either because this needs to be rationalized. So we'll multiply the top and the bottom by the conjugate of 2 plus square root of 2. And that means we'll have 2 minus square root of 2, top and bottom. Okay, distributing in the top, square root of 2 times 2 gives me this. Square root of 2 times square root of 2 gives me minus 2. In the bottom FOIL method, 2 times 2 is 4. The outer term and the inner term are going to cancel out. So I'll skip over those, and then last times last is minus 2. In the denominator, 4 minus 2 is 2. Alright, now look at your top and your bottom. You've got 2 here and here and here. That means that since everything can be divided by 2, we should do that. And that's going to leave us 1 square root of 2 minus 1 all over 1. So here I've got my square root of 2 minus 1. I did not write the denominator though, since it's simply a 1, we really just don't need it. And here's another example for us. This one maybe has a little more to do. Given that the cosine of s equals 2/3, where s is between 3 pi over 2 and 2 pi, let's find the cosine of s over 2 and the sine of s over 2 and the tangent of s over 2. Okay, so we'll start with cosine, I guess. Let's take a look at the cosine of s over 2 formula. Here it is. Alright, so I know that the cosine of s is 2/3. So I'm going to be replacing the cosine of a here with 2/3. Alright, now I need to reduce that complex fraction, so I'll multiply everything by 3. And that's going to give us, when we distribute the 3, it's going to give us 3 plus 2 in the top, and in the bottom 6. So the 3 plus 2 is going to make 5. And we're left with plus or minus the square root of 5/6. Now, this is the right value, but it's not in a very nice form. So first let's decide on our sign. We know that s is between 3 pi over 2 and 2 pi. In other words, s is in quadrant 3. If I need to know the location of s over 2, I'll have to divide this by 2, which means I have to divide both ends by 2. Okay, so this becomes 3 pi over 4, and this becomes pi. And 3 pi over 4 is 135 degrees. So this is telling me that s over 2 is between 135 and 180. That makes sense. If s is between 270 and 360, then s over 2 should be between 135 and 180. And that means that s over 2 is in quadrant 2. And that means that the cosine should be negative. Okay, now this is nice, but it's not in a very nice form. This fraction needs to be rationalized. So I will split up my fraction so that top and bottom have their own radical, and then let's rationalize that, and we'll have in the top square root of 5 times square root of 6 is square root of 30, and in the bottom square root of 6 times square root of 6 is 6. And this finally is an acceptable form because it's rationalized and there are no complex fractions. So that's the end of cosine of s over 2. Now let's go ahead with the sine of s over 2. So we'll take a look at the sine of s over 2 formula. If we substitute s over 2 in place of a over 2, then we'll substitute s in place of a, and the cosine of s is 2/3 again. And again, we have to not rationalize, but simplify this complex fraction. So I'll multiply the top by 3 and the bottom by 3. That will give us, when we distribute the 3 minus 2. And in the denominator, 2 times 3 is 6. And so 3 minus 2 is 1. And our answer is the plus or minus the square root of 1 over 6. But again, we have to decide on the sign. We've already figured out that s over 2 is in quadrant 2, and sign values in quadrant 2 are positive. So now I'm going to drop the plus or minus because I've decided that it should be plus. And we'll split up the 1 over 6 so that top and bottom each have their own radical. We'll rationalize that fraction, and we'll come up with square root of 6 over 6. And so that is the sine of s over 2. And now let's do the tangent. So we pull out just any old tangent formula. I'm going to go ahead and use the radical one in this case, since I don't have the sine of s available, and we could find it, but we're given the cosine, so let's go ahead and use the formula that only requires us to know cosines. So I will plug in the 2/3 in place of cosine of s, and again we'll eliminate the complex fraction by multiplying everything by 3. And so if I distribute the 3 under the radical, I get 3 minus 2 for the top, and for the bottom 3 plus 2. And so we're left with, we've already figured out that since s over 2 is in quadrant 2, that tangent value should be negative. So that's going to be negative 1 over 5. Break it up and rationalize it, and you're left with negative square root of 5 over 5. And one last example that we'll do together. Find the tangent of theta over 2, given that tangent is square root of 7 over 3, and theta is between 180 and 270. In other words, theta is in quadrant 3. Well, let's take a look at the tangent of theta over 2 formula. And there are 3 different varieties, again, so we get to choose which variety we like. One of them calls for cosine of theta, the other 2 both call for sine and cosine of theta. We only know tangent of theta, so we'll have to figure out the sine and the cosine. Since we know theta is in quadrant 3, and we know that tangent is vertical over horizontal, we know that the vertical side will be square root of 7 and the horizontal side will be 3. And then if we add the squares together and do the square root, we'll find the hypotenuse. So that's going to be 7 plus 9 is 16. Square root of 16 is 4. Okay, now I can say that the sine of theta is negative square root of 7 over 4, and the cosine of theta is negative 3 over 4. Both negative because we're in quadrant 3. And so let's go ahead and plug into one of our formulas. And again, I choose the sine over 1 plus cosine. So that's going to be negative square root of 7 over 4 all over 1 plus negative 3 over 4, or 1 minus 3 over 4, either way. And let's not rationalize, but again, simplify this complex fraction. We will multiply both top and bottom by 4, and that will leave us negative square root of 7 in the top, and in the bottom 4 minus 3, which is 1. So we end up with negative square root of 7.